Hello and welcome to another calculus video. Big day here in Calc. We're starting Chapter 6, and this is where our journey is going to end in high school. We're definitely going to get through the first three sections here. Because of the COVID and all the stuff this year, we're probably not going to get to 6.4, which is fine. To get through the AP test, we should just do through 6.2. As long as you know the disc and washer methods, you'll be fine. Some more complicated problems might be made easier if you know this shell method. So I always like to get the shell method in to the end of this class also. All right, the assignment for this section, there's only one problem out of the book. That's number 22 on page 414. The rest of the assignment is all on WebAssign. And here we go. In earlier sections, we found the area under a curve, and the bottom of that area was usually the x-axis. In this case, what if we want to find the area between a couple of curves? Well, it's not that much different, and it's not very difficult at all. So the book says with a few modifications, we can extend the application of definite integrals from the area of a region under a curve to the area of a region between two curves. Consider two functions f and g that are continuous on some interval from a to b. Also, the graphs of both f and g lie above the x-axis. The graph of g lies below the graph of f as shown in figure 6.1. So here we've got the f function is the darker one, it's on top. We've got the g function is the lighter gray one, it's on the bottom. And we want to find the area between the curves from a to b. We can geometrically interpret this area as of the region between the graphs as the area under the graph of g subtracted from the area under the graph of f. So if we look here, so here is all the area that is under f, the entire area here. And if we find this area here and subtract it, we'll be left with the area that's in between the curves. So if we look below the pictures, we've got some integrals set up there. So the area between f and g is equal to the area under f, so that's our integral from a to b of f of x dx. And we're going to subtract out the area under the g curve. That's the same integral, or the same upper and lower limits, a to b, but now of g of x. So if we're going to subtract them here, top minus bottom, the function on the top minus the function on the bottom, we get the area between the curves. So here's our integral from a to b of quantity f of x minus g of x dx. So it's the integral of top minus bottom. So to verify the reasonableness of the result as shown in the figure, we can partition that interval from a to b into some number of subintervals, each of with delta x. Then, as shown in the figure over here, we could sketch a representative rectangle. Now, I know you might be thinking, geez, I don't want to go back to doing summation notation and all that. We're not. But this idea of a representative rectangle is huge in this section and in the next couple. So it's always nice if you're not going to draw a picture to at least visualize. And notice here I'm going to highlight it in red ink. This is our representative. That's not ink, that's a highlighter. Here we go. Oh, it's supposed to be red. There we go. So what I'm blocking off here in red ink, that is our representative rectangle. And notice the top of our rectangle is touching the f curve, and the bottom of the rectangle is touching the g curve. So it's nice to draw the graph and draw a little representative rectangle. And always remember that we're going to do an integral from a to b, and we're going to do top minus bottom. What function touches the top of this red representative rectangle minus what touches the bottom of the red representative rectangle? And I'm not going to read through. You know, here again, they're just showing as your norm goes to 0. They're just bringing it back with the summation. And then they translate from the summation notation back to our definite integral form, which we've come to know and love over the past few weeks. So we got our definition here in the box. The area of a region between two curves. Let's read our setup, our if statement. If f and g are both continuous on an interval, and g is less than or equal to f for all x's in the interval, that just means g is on the bottom, f is on the top. Then the area of the region bounded by the graphs between f and g and the vertical lines a and b is, here's our definite integral setup. We set up a definite integral from a to b of quantity f of x minus g of x dx. It says here in the figure 6.1, the graphs of f and g are shown to be above the x-axis. That's back here. F and g are both completely above the x-axis. Does that always have to be the case? This, however, it's not necessary. The same integrand, f of x minus g of x, can be used as long as both functions, f and g, are continuous and g is underneath f for all x's in that interval. This is summarized geographically in 6.4. Notice in 6.4 the height of the representative rectangle is f of x minus g of x, regardless of the relative position of the x-axis. And what's this insight? Finding the area between of a region between two curves is tested on both AB and BC exams. Let's see here. They were talking about figure 6.4. Yeah, here we go. It doesn't matter if both graphs are above the x-axis. Here we've got our top function is above the x-axis. Here our bottom is below, but that's fine. And then it wouldn't be a big deal if we have both functions completely under the x-axis. Here's f is below the x-axis as well as g. So no matter what, we can always find the area between those curves. It doesn't matter where we are oriented in the plane. So back in 6.1, blah, blah, blah. Yeah, I guess we already read that. Here at the bottom, representative rectangles are used throughout this chapter in various applications of integration. A vertical rectangle of width delta x implies integration to the x-axis. A horizontal rectangle of width delta y implies integration to the y-axis. And that's another good thing to point out here. When you are setting up an integral, another good reason to at least visualize this representative rectangle is we are always perpendicular to the axis of integration. Here we are perpendicular to the x-axis, so our functions will have x's in them and we'll have a dx differential. We might have the case, I'm going to use blue ink here, maybe we'll have a horizontal rectangle. And we will always do that as, what is touching the right minus what is touching the left side of that representative rectangle. And again, it is perpendicular to the y-axis. So if our representative rectangle looks like this, we are perpendicular to y. That means our function will have y's in it, and we will have a dy differential. And do we get to do one? Oh, finally, here we go. Now, of course, example 1 starts, it's a nice slow pitch right across the plate. And it says here, find the area of the region bounded by the graphs of x squared plus 2. That is this parabola opening up. I'll highlight it in red. So there's our first function. And then we've also got y equals negative 1x. That is this downward sloping line. I'll hit in blue. So we want to find the area of the region between those graphs. And between x is 0 and 1. So we can see here on my slide, that is this sort of pink shaded region. So what we just learned is area is going to be an integral from a to b of the function that touches the top of our rectangle minus the function that touches the bottom. And let me get this out of the way here. Minus what touches the bottom. And in this case, since here I didn't drag it completely out of view, our representative rectangle is perpendicular to the x-axis. We're going to have a dx differential on there, and that means all of our functions should be written in terms of x. All right, let's start filling in some of these unknowns. So they gave us the a and the b. They handed them right here. X equals 0, that's our a. X is 1 is a b. So 0 to 1 on our definite integral. Now, what function is touching the top of our representative rectangle? I'll switch back to red ink for that. That is the x squared plus 2. So that's this part here, top. And now we're going to subtract. I'll switch to blue ink for what's touching the bottom of this rectangle. And the function we're hitting at the bottom there is that straight line. And that straight line's equation is y equals negative x. So that's going to be minus a negative x dx. So there's our setup. Oops. So let's simplify that as much as we can and then anti-derive and see where it takes us. Let me get this out of here. So we're still going to have our integral symbol from 0 to 1, where our first term is going to be x squared. X squared. This minus the negative, that's going to turn to a plus, so we're going to have a plus x. And then at the end we'll have our constant, a plus 2, and a dx. Okay, so we're all set. It looks like we are ready to anti-derive. So let's see here. X to the second is going to become x cubed over 3. Plus x to the first becomes x squared over 2. And then we've got a plus 2x. Our integral symbol is now migrated to the other side, turns into a bracket with our lower and upper limits on board. And these are probably about the easiest limits to work with, 0 to 1. So let's see what happens when the 1 jumps in. I'll use red ink here. So that's going to be 1 cubed over 3, or a third, plus 1 squared over 2 is a half. And then we've got plus 2 times 1, that's a plus 2. Now the fundamental theorem says we are going to subtract as a quantity when our lower limit hops in there. So that's going to be 0 cubed over 3 plus 0 squared over 2 plus 2 times 0. So that's a wash. They all just washed out. But it is always good to check. Don't just assume your lower limit of 0 is just going to 0 out. And there we go. I guess if we add that up, we're going to get 2 and 5/6. 2 and 5/6. Or if you prefer impropers, that would be 17/6. And I guess since we're talking about area here, they didn't give us any units in the problem. But just so I know in the back of my head, that's going to be some units squared. Because what we were hunting for was, in fact, area. All right. And let me point out something else on this graph here when I pull it down. Notice these functions never intersect, and they're never going to intersect. You know, this parabola will go up steeper. This line is just going to stay nice and constant. So the line and the parabola are never going to intersect. But that's not going to stop us from finding the area between them across some interval. All right, let's see here. Example 2. Area of a region between intersecting curves. In example 1, those graphs do not intersect. The values of a and b are given explicitly. They're just handed right to you. A more common problem involves the area of a region bounded by 2 intersecting graphs, where a and b must be calculated. So now here we've got a graph 2 minus x squared. That is our downward opening parabola. We've got the line y equals x. That is this line sloped through the origin. Notice that they did not tell us where to begin and end our integration. Now, because they gave us such a great graph, it would be real easy to say, well, I'm going to eyeball that, and that sure looks like a 1. And I'm going to eyeball that one, and it sure looks like a negative 2. That is a dangerous road to go down. There is one of the problems in the assignment where if you try to eyeball it from the graph, you're going to get the wrong answer. I did the first time I attempted the problem, and I'll make sure to give you a little warning on that one. So how do we figure out where 2 graphs intersect? We're going to set them equal. So I'm going to write here intersect, question mark, set them equal. If we set the graphs equal to each other, we will find their common points. And really all we need here are the x values of their common points. So I'm going to set 2 minus x squared equal to positive x. And since my x squared is negative on this side, I'm going to move the x squared over, or it's now a positive x squared. We have a plus x. And then we'll bring over the 2 by subtraction, so now it's a minus 2. And we've got a quadratic equal to 0. So it sure looks like we're going to factor that. x times x, factors of 2, 2 and 1. We want them to add up to plus 1, so that's a plus 2 and a minus 1. If we set each factor to 0, we're going to get x equals negative 1, positive 1, and we're also going to get x is negative 2. So 1 and negative 2 are our intersection points. So if I drag the graph back up here, remember we can talk about finding the area between curves as an accumulation. So we're going to start here at negative 2, and we'll start working our way along between the functions, accumulating this area as we go. And then we're going to stop here at that value of x is 1. So we can set up an integral. And we are going to go from negative 2 at the bottom to 1 at the top. And now we're going to put our functions in here. Remember, top minus bottom. And if I bring the graph down again, I'll hit in red. Here's the top of our representative rectangle. And that is touching the 2 minus x squared function. And then we're going to subtract the function touching the bottom of it here in blue. And that is just y equals x. So minus x. And I guess to make this perfect, I'd need some groupers around there and put a dx on it. Okay, let's do a little algebra here and get this ready to integrate. Negative 2 to 1. So let's see, our leading term is x squared, and it's a negative x squared. And then we're going to have a minus x. And then we're going to have a plus 2. And I guess I should still got to put my dx on there. dx. All right, time to antiderive. We finally get a chance to do a little calculus here. So let's see, negative x squared becomes negative x cubed over 3 minus x squared over 2 plus 2x. And now our bracket is over here from negative 2 to positive 1. All right, I'll use red for my upper limit. So this 1 is going to hop in there. That's going to be a negative 1 cubed is 1 over 3, negative 1/3. Minus 1 squared is 1 over 2, that's a half. And then plus 2 times 1 is 2. So there's our upper limit. And now we are going to subtract as a quantity our lower limit, negative 2. Now be careful, we've got this negative out here. When I plug the negative 2 in and cube it, that's going to be a negative 8, and then this negative is going to hit it and make it a positive 8, 8/3. Real easy to lose track of that negative and get the wrong sign on there. Minus negative 2 hops in for this x squared. Negative 2 squared is positive 4, so that's going to become minus 4/2. Or I guess we could just replace that with a 2. And then the negative 2 is going to hop right in here. Negative 2 times 2, that'll turn into a minus 4. Now, we do want to get that down to a single beautiful number. And I'm going to do it like this. First, I'm going to distribute this negative. I'm going to turn that into a 2. So we've got negative 1/3 minus a half plus 2 minus 8/3. This becomes a plus 2, and this becomes a plus 4. So now I'm just going to collect my whole numbers. Here we've got 2 and 4. That adds up to 6. And 2 more here, that becomes an 8. So I've taken care of those. I've got a negative 1/3 minus 8/3 more. That is a negative 9/3, and 9/3 is 3. So that becomes, get out of there, 8 minus 3 minus another half. So 8 minus 3 is 5. 5 minus a half is 4.5. Or if you prefer improper, 9/2. Okay, not too bad. Let's see what Mr. Larson has for us next. Intersecting graphs, but now it's trig, because you know we're not having fun unless we're doing some trig function stuff. So the sine and cosine waves intersect infinitely many times, bounding regions of equal area. As shown in the figure, find the area of one of these regions. So think back to way back when we were graphing in pre-calc. Sine wave starts at the origin and rolls out. Cos wave starts at a peak and then rolls out. So we've got a couple intersection points here and here, and we've got this area between it. Now, as the graphs continue to roll out, this blue area has the same region, and then those are going to repeat for infinity to the left and the right. So we can find the area between one of those regions, and it'll be the same for all the others. But first, we need to figure out where they intersect. If you look at this graph, we hit here. That's going to be somewhere here on the x-axis, and also here on the x-axis. So we need to ask ourselves, and this would be real easy if you have a unit circle sitting in front of you, we need to find those intersection points. So where is sine x exactly the same as cos x? Or think on your unit circle. There's a spot right here in the first quadrant where sine and cos are both positive root 2 over 2, and that occurs at pi over 4. And then in the third quadrant, down here, there's a point where both the x and the y coordinates, the sine and the cos, are negative root 2 over 2. That occurs at 5 pi over 4. So there's our intersection points. That is where we will begin and end our accumulation of area. So okay, let me move this up here so we can see it. All right, first piece of the puzzle. The number at the bottom is quarter pi. Number at the top is 5/4 pi. Now we need to set up our integral top minus bottom. So again, back here to the figure. What is touching the top of our representative rectangle is the darker line. If I follow it back, it started at the origin. So that is our sine wave, sine x, minus, we want the one that's touching the bottom, and touching the bottom here in blue, that is our cos wave. And we'll slap a dx on there. All right. So let's see. We got to antiderive. Antiderivative of sine x is negative cos x. Derivative of cos is sine. So that just becomes a minus sine x. And we now have a bracket over on the right with quarter pi at the bottom, 5/4 pi at the top. And move this about up here, and this over here. Okay. Now be careful, we got negatives here. Fundamental theorem's going to have a negative, so I'll start with color coding, use red here first. So we're going to get these with 5/4 pi's in there. So we're going to have a negative cos of 5/4 pi minus a sine of 5/4 pi. And then fundamental theorem says we're going to subtract as a quantity. Now we plug in the same ones with the bottom limit. Quarter pi is going to jump in there. So that's a negative cos quarter pi minus the sine of the same quarter pi. Okay, now we go to the unit circle. So we've got this negative right here. And then the cos at 5/4 is a negative root 2 over 2. That's a 2. And then we've got minus sine at that is also a negative root 2 over 2. And then here, let's distribute and do this sort of at the same time. This minus the negative, that is going to turn into a plus. The cos at 1/4 pi is root 2 over 2. And the negative here will also distribute to this negative. So that's going to be plus the sine at 1/4 pi is also root 2 over 2. So let me get some of this out of the way. There we go. So let's see. And right here at the beginning also, this minus the negative, that's going to turn to a plus. Same thing here. Minus a negative is going to turn into a plus. So look what we got here. We're just adding up 4 fractions. Do we have a common denominator? You betcha. It's 2. Our numerator has root 2's. How many of them do we have? 1 root of 2, 2 roots of 2, 3 roots of 2. We got 4 roots of 2. 4 root 2. So at the lead here, we've got these coefficients we can divide. 4 divided by 2 is 2. Square roots of 2. If you've ever wondered what is the area between those intersecting sine and cosine waves, each of these regions has the exact area of 2 times the square root of 2 square units. Okay, 2 more examples to go, or it might be 3. I think the last one's not much of an example. Okay, we've seen curves that never intersect, curves that intersect just twice so we can find the area of region between them. What about curves that intersect at more than 2 points? Ooh, and I guess there's some stuff to read up here. Let me shrink this down a little bit. To find the area of a region between 2 curves that intersect more than 2 points, first determine all points of intersection. Then check to see which curve is above the other in each interval determined by these points. So in this case, we want to find the area of the region between these 2 graphs. Now, even if we never see the graphs, we can investigate and find all intersecting points. If you did graph it, here's what it's going to look like. Now, notice I'm going to use red ink here on the left. In this section, before the graphs intersect at the origin, we've got the darker one is touching the top, the lighter gray function is touching the bottom. After they intersect at the origin, that flip-flops. So now the lighter gray one is on top and the darker inked one is on the bottom. So when they flip-flop in the middle, that means we're going to have to set up 2 different integrals. Because remember, it's always top minus bottom. When your top and your bottoms flip, you're going to have to just set up another integral. So the first thing we need to do is find all intersection points. And that means we're going to set these 2 functions equal to each other. 3x cubed, oop, that's a terrible exponent. That's not much better, but it's staying. Minus x squared minus 10x. We're going to set that exactly equal to negative x squared plus 2x. All right, well, let's set it equal to 0. If I add x squared to both sides, this becomes a plus x squared, and those are going to 0 out. And I'm also going to get rid of this plus 2x by subtracting 2x. So we're going to do a minus 2x also. So now this is going to be equal to 0. And what is going to equal 0? We've got 3x cubed. The x squareds cancel out. And then we've got a minus 12x, and that's equal to 0. So let's see, we can factor out a 3 and an x. And that's going to leave us x squared minus 4. Now we could just set those equal to 0, or I'm just in the mood to factor one more time. So x squared minus 4 becomes an x plus 2 and an x minus 2. And that's equal to 0. So now we can set each of those 3 factors to 0. So if I set 3x equal to 0, I get x is 0. If I set x plus 2 to 0, I get x is negative 2. And if I get x minus 2 equals 0, I'm going to get x is positive 2. So we know that this is where we intersect. Negative 2 we intersect once, we hit again at 0, we hit again at 2. Now we could, if we were never given the graph, how would we figure out which one's on the top or the bottom? Well, we'd pick a number from each interval and put it into both functions, f and g, and see which one comes out as the bigger y value. Like if we look here on the graph, if I put negative 1 in, the darker graph is going to have a bigger output than the lighter graph. So I know that that one is on top. F is on top. If I put 1, positive 1, into both of the functions, the other function, the g of x function, will have the bigger output. So even if the graph is not handed to you, you can do this flying blind just by plugging in a test value. See which y value is bigger. So let's think about when we set up our integrals. We're going to have 1 that goes from negative 2 to 0 with the darker function on top, f of x, and then we're going to go from 0 to positive 2 with the f of x on the bottom. So it's going to be g of x minus f of x. Okay, get this out of here. So if I had more room, I'd write A equals, area equals, and we're going to set up our first integral. And let me color code this red and blue. Red first. And red is going to be this first piece of area here. So this part. So we're going to start accumulating at -2. We are going to go to 0, and now we need to set up top minus bottom. The function on top here is the cubic. 3x cubed minus x squared minus 10x. And then we're going to subtract the function on the bottom. That's this one up here, -x squared plus 2x. -x squared plus 2x. I'll stop that one and give it a dx. So that red integral represents this first piece of area. Now when we switch at the origin, we're just going to reverse the order of our functions, that they're subtracted. And also, of course, we're going to have different limits. So here, this is our first bit of area. We're going to add to that another integral that goes from 0 to 2. And now I'm just going to take these functions and flip them. Those are just going to be in different spots because the top and the bottom have switched. So now here first goes the -x squared plus 2x. And then we're going to minus the cubic. 3x cubed minus x squared minus 10x. And that gets its own dx. All right. Now what I'm probably going to have to do here is shrink this up a little bit. Like, oh, it's not going to let me. There we go. Oh, shoot. I need to hide this so I don't shrink it by accident. Good enough. There we go. Oh, that's supposed to be at the bottom. Yeah, -2. There we go. Sorry about that. Okay. So before we antiderive, let's clean those up a little bit. I'm going to have my integral -2 to 0. And let's see, our biggest term there is 3x cubed. 3x cubed. We've got a minus x squared, and this is going to be minus a negative, so that's going to change to a plus x squared, so those are going to cancel. And then we've got a negative 10x, and this negative is going to distribute and make that a minus 2x, so we've got a minus 12x there. And that gets a dx. And now we're going to add to that the next integral that picks up at 0 and goes to 2. Now let's see here, when we distribute this negative, now our leading term is a minus 3x cubed. See here, we're going to distribute the negative to make this a plus x squared. Hits the negative x squared, that's still going to cancel. And now we've got a positive 2x plus 10x, so now it's a plus 12x. And that gets a dx. Okay, we've done a lot of work, and now we finally get to do a little calculus. And then it's some more algebra and arithmetic. So enjoy the calculus. So let's see here in red, let's antiderive. That's supposed to be red. So we're going to raise that to 4th power and divide by 4. So that's going to be 3, oops, get back there. 3x to the 4th over 4. Minus, raise that up to squared, divide by 2. That's going to be a 6x squared. And we will evaluate that integral from -2 to 0. And then we're going to add to that another integral. See here, raise the power by 1, divide by the new power. That's going to be a negative 3x to the 4th over 4. And then this is going to be a plus, raise that to squared, divide by 2, 6x squared. That's supposed to be a squared. And we've got a different bracket here with a 0 to 2 on it. Okay, time to evaluate. Here, now this is kind of odd, 0 being our upper limit, so 0 is going to hop in and zero out that first fraction, minus 0 is going to zero out the second one, and then we're going to subtract as a quantity. See here, when we plug in the negative 2 to the fourth would be 16, times 3 is 48. Divide that by 4, that's going to be 12. Negative 2 hops in here, that's going to be squared to a 4. Times 6 is 24. So minus 24. And I should, to keep with my color coding, have made that red. And we'll shrink that up just a little bit. We're going to add to that, plus. Let's see here, when this 2 jumps in, we're going to get the same answer on the other side. It's going to be 12, but this minus is going to get attached. So that's going to be a minus 12. And then when the 2 jumps in here, that's going to be a plus 24. And then we're going to do our lower limit, subtract. Lower limit jumps in, 0 plus 0. So let's see here. Distribute here, you're going to get a negative 12 minus 24, so that red stuff is a negative 36. Ooh, hold the phone there a minute, because that is going to turn to a plus 24 when we distribute. I almost messed that up. So that's going to be a negative 12 plus 24, so that's going to be a 12 plus 24 minus 12 is 12, and then 12 plus 12 is 24. So there's the area between those intersecting curves. Okay, what's next? When the graph of a function of y is a boundary of a region, it's convenient to use representative rectangles that are horizontal, and find the area by integrating with respect to the y-axis. So that means our representative rectangle will be perpendicular to the y-axis. In general, to determine the area between two curves, we can use, if we have vertical rectangles perpendicular to the x-axis, we're going to do our upper and lower limits will be numbers on the x-axis. It will be top curve minus bottom curve, and a dx differential. So everything is in terms of x. Our limits come from x. Our functions have x's in them. We have a dx differential. On the other hand, if we have some curves and our representative rectangles are horizontal, we are now perpendicular to the y-axis. So our numbers, our upper and lower limits, will be numbers on the y-axis. Our functions will have the variable y in them, and we'll have a dy differential. So again, it's always good to draw or at least mentally think about that representative rectangle to figure out what variable you should be using. And here we go. Find the area of the region bounded by these functions. X equals 3 minus y squared. And we have x equals y plus 1. So let's see here. I guess, we don't have to find the intersecting points because they did just hand them right to us. So if we look here, the top is at a y value of 1, and the bottom intersection point is here at negative 2. So that tells us the numbers are going to go on our definite integral symbol, negative 2 at the bottom, positive 1 at the top. And now we're going to subtract our functions. Remember, in this case, it's going to be right minus left. So here's our representative rectangle. The right side of that rectangle is touching the 3 minus y squared. 3 minus y squared. And we're going to subtract the function that's touching the left end of the rectangle. And here I hit that in blue. That is just our line y plus 1. Y plus 1. And we're going to put a dy on there. Again, notice every number up here, everything has y's in it, or the negative 2 and 1 came from the y-axis. Our functions have y's in them, and we have a dy differential at the end. So let's do a little algebra to get ready for the calculus. So we've still got negative 2 to positive 1. Our biggest exponent 1 is that y squared, and it's a negative y squared. When we distribute this negative, that's now going to be a minus y. And if we keep distributing, that's going to be a minus 1, and we still have a 3 at the beginning. 3 minus 1, last I checked, is 2. And we'll put our dy on there. Okay, we've done a bunch of work, and now we're ready to enjoy a little calculus. So just a nice power rule. We are going to raise the power by 1 and divide by the new power. Raise the power by 1, divide by the new power. The constant gets a variable attached. And we've got negative 2 at the bottom, and we've got positive 1 at the top. Okay, another one, again, remember to be very careful with those negatives. So here in the first one, we've got this negative here, that's a minus. And then when the, that's right, 1 jumps in first. So I was getting a little ahead of myself. So 1 cubed is 1, so that's 1/3 negative. Minus, when the 1 jumps in there, that'll be 1 squared over 2, or a half. And then plus, 1 times 2 is 2. Fundamental theorem says we will subtract as a quantity. This negative 2 jumps in right there, and that becomes a negative 8. But be careful, I'm going to use black ink, we had that minus out there. And now when we plugged in our lower limit, this is going to become a negative 8/3. And when the negative 2 jumps into the y squared, that'll be a positive 4 over 2. So that's going to be minus 4/2. And when the negative 2 jumps in the last one, 2 times negative 2 is minus 4. So we got, yeah, that looks good. And let's distribute the negative and collect what we can. So we've got negative 1/3 minus 1/2 plus 2. This will hit, well, this first becomes a positive 8/3 because those two will turn into a positive. But then this minus jumps in, so that's still back to minus 8/3. This will hit and become a plus 2. And the negative will hit here, and that will become a plus 4. So I'm going to work my way back up. I'm going to start with my whole numbers. 2 plus 2 plus 4, that's 8. 8. Minus, we got a negative 8/3 and another minus 1/3. That's negative 9/3. That's a minus 3. And then we've got this leftover little minus 1/2 in there. So 8 minus 3 is 5. 5 minus 1/2 is 4.5, or 9/2. And there we go. We integrated this time to the y-axis. Now let me show you something too here. If I bring the graph back down, we could have done this with the other method, but it would have been a much more difficult one. Oh, I guess they already got this in here. Notice when we were doing this one, our representative rectangle started down here at the bottom intersection point, and as it went out, it grew and then it shrunk back down until we got to this point. So as we went between those curves, the right side of the rectangle was always touching this curve I'll hit in red. The blue was always touching this one I'm hitting here, or the black, or the left-hand side always hit the blue curve. And that was true all the way across. Look if we had done it the other way. If we tried to go to the x-axis, we would have started out fine. Down here, the top of our rectangle is hitting the line. The bottom of the rectangle is hitting the parabolic curve. But look what happens after this 2, 1 point. That's when the line goes up and out of the picture. This representative rectangle here, the top of it is touching the parabolic curve. The bottom of it is also touching the parabolic curve. So we'd have to do more work and break the parabolic curve into its positive radical and negative radical form. If we can do another method to get around that, I highly recommend it. We will see in an upcoming section where we're going to find it 2 different ways and show that they are equal. But in this case, it's easier to go to the y-axis than the x-axis. Yeah, and here's where the book goes through the computations of that. Here's what happens at the other side. We've got our positive radical minus a negative, so that turns plus, of that same radical. So we've got two of them. We go through the computations. There's much more arithmetic, but we do get the same correct answer. Now here, I've been talking about integration as an accumulation process for a while. Here's some more to reinforce that. The book says in this section, the integration formula for the area between curves was developed by using a rectangle as the representative element. For each new application in the remaining sections, an appropriate representative element will be constructed using pre-calc formulas that we already know. Each integration formula will then be obtained by summing or accumulating those representative elements. So we've seen this before. We take a known formula from pre-calc or even geometry. We figure out the representative element. That will lead us to a new integration formula. Like back our known pre-calc formula, the area of a rectangle is base times height, height times width. The change in area is top minus bottom, f of x minus g of x, delta x. And then we just turn that into a good old definite integral. So find the area of the region bounded by the graph of 4 minus x squared in the x-axis. Describe this as an accumulation process. So I guess if we just go by the pictures here at the bottom, there's nothing really much to write down here. There. Okay, so we've got 4 minus x squared. That's our parabola opening down. We hit it positive and negative 2 on the x-axis. So notice here, we're going to start right at negative 2. We're at the starting line. We have yet to begin to run the race. So the upper and lower limits are the same, negative 2 to negative 2. Remember that theorem, no matter what function's here, we've accumulated 0 area. Okay, now we're going to start moving that representative element across our region. So we're starting here again from this point, and now we're moving our way to the right. We're now here at negative 1. So we can go from negative 2 to negative 1 of our function, antiderive and evaluate. We're up to 5/3 square units. So we went from negative 2 to negative 1 and accumulated 5/3. Let's go to the y-axis. So we keep accumulating area till now we're at the y-axis. So that's negative 2 to 0. We have our same function. Antiderive and evaluate. We're now at 16/3 of accumulated area. Let's keep going. We move more along to x equals positive 1. We have accumulated more area as we go. So now our limits are negative 2 to 1, and now our area is 9 square units. Let's keep going all the way. Let's finish this off. From negative 2 to positive 2 of our same function, that area is 32/3. Again, I like to always think of this, we're working left to right. We're starting here and accumulating area. And as I scribble to the right, we are accumulating that area as we go. And then it gets less and less and less, and boom, we're all done. The red area is 32/3 square units. And that is the end of section 6.1. Next time I see you in class, we'll try some of these odd problems here. They look like they're just so much fun. I cannot wait. I hope this video was helpful.